Okay, so today we're going to talk about the 45-45-90 triangle. So previously we learned about the 30-60-90 triangle. That's one of our special right triangles. And we talked about how all triangles that are similar will have the same ratio of sides. And with a 30-60-90 triangle, the ratio of those sides is 1√3, 2. So now I want us to talk about the next special right triangle and see if you can find the pattern for the ratio of the sides of a 45-45-90 triangle. So just like we did in class, I'm going to go ahead and not talk for a little while. And as I'm filling these out, I want you to think about if you could figure out the other numbers on your own. Okay, so I hope that you enjoyed the sounds of my dog snoring in the background, which you may have heard, but I also hope that you noticed that we have a ratio for our set of similar triangles with the 45-45-90 degree angles. So let's go ahead and put this on our summary sheet. On our 45-45-90 degree angles, we know that we have a right triangle and we know that our angle measures are 45 degrees, 45 degrees, and 90 degrees. And with that 45-45-90 degree angles, across from each of the 45s has a ratio of 1, and across from the angle of 90 has a corresponding √2. So when we take a look at that, that gives us an exact value for any of the sides, only having to know one side of that right triangle. Okay, so let's go back into our booklets together. We're going to do some practice. So if you would open to page 22, and we're going to look at the bottom here. And so I want you to just take a couple minutes and try question 1. And then when you're ready to check, and so pause the screen. And when you're ready to come back and check your answers, go ahead and unpause. Okay, so hopefully you've taken a moment. And when we take a look at this, I see that these are my 45-degree angles. The sides opposite them should be congruent to each other. So we have 13, 13, and then x is 13 root 2. Here we have our congruent sides, which are opposite our 45-degree angles. So that means I have 10, 10, and 10 root 2. This one across from my 45-degree angle is 10 root 2. So across from my other 45-degree angle is also 10 root 2. And then to get the hypotenuse, I'm going to take 10 root 2 and I'm going to multiply it by root 2. Now when I do that, I get 10 root 4. And the square root of 4 is just 2. So 10 times 2 is 20. Okay, take a moment. Try question 2, parts A, B, C, and D. Pause the screen, and when you are ready to check your answers, come on back. Okay, so taking a look here, across from my 45-degree angle, I have 2 root 7. So this is also 2 root 7. And then my hypotenuse will be 2 root 7 times square root of 2, which is 2 root 14. Now that we've gotten to a just slightly more complicated one, I do just want to show you that you can still continue to use the proportion method we talked about in class. You can set up your 45, 45, 90 ratios, which are 1, 1, root 2. And you can put the information you have. So 2 root 7 is across from the 45. And x is across from the 90. And now I have an equation which I can solve algebraically. So notice when I cross multiply, I get x equals 2 root 14, just like I did by reasoning through it. I want you to use the fastest method that you can use while still being accurate. So if you are able to be accurate here, just reasoning through, great, that's the method that you should use. But if you're getting stuck, I want you to use this method so that you can be accurate. Okay, so I'm going to show you that method again here with this one, because you might be looking at this saying, I don't know how to work backwards and get to this spot. So if that's the case, let's go ahead and just set up our ratios. 45, 45, 90. Across from the 90, we have our ratios, 1, 1, root 2. Across from our 90 is 52 root 10. And my x is across from a 45. So here's my equation. I go ahead and cross multiply. I have 52 root 10 equals root 2 times x. To get rid of that root 2, I'm just going to divide by it. But if I do that on one side, I also have to do that to the other. And then often people get a little bit stuck on the algebra, what to do here. I have 10 and 2 both inside the roots. Those will divide, while 52 stays outside the root. So I'm going to have 52 root 10 divided by 2 is 5. And so that's my final answer. Notice how with this problem, I don't think I lost really much time by using this method. In using this method, I think it was just as efficient as kind of working backwards. And I, was sure that I was being accurate as well. Okay, let's do another one like this. I have 45, 45, 90. I have 1, 1, root 2. 20 is across from the 90, and x is across from the 45. So here's my equation. 20 equals root 2 times x. And to get rid of that root 2, I'm going to divide by root 2 on both sides. and 20 over root 2 is my final answer. If you've learned how to rationalize the denominator before in other classes, that's awesome. You do not have to do that in this class, so I'm just going to leave it as 20 over root 2. All right, hopefully you've tried this last one. When you get this last one, you should get x equals 18 over root 2. It should follow the exact same process you did here. So if you're feeling stuck, I want you to try it on your own again by using this exact method. Okay, let's look at some more advanced questions with this. So I want us to now think about when we go beyond just the basic triangle. So this says the perimeter of a square is 28 centimeters. So I'm going to sketch my square. Here's a square. And when I have a square, I have 4 congruent sides. So I have 28 divided by 4, that's 7, 7, 7, 7. And it wants me to find the exact length of the diagonal. Previously, when we did our quadratics unit, we would have done Pythagorean theorem and figured out this diagonal. But now what I see is that I have a 45, 45, 90 triangle. And very quickly I can say, oh, my diagonal is 7 root 2 centimeters long. All I had to do was use that ratio. Excuse me. All right, let's take a look at question 4. Now I have 2 attached triangles. When I take a look at that, I'm going to go ahead and say, okay, well, it's a 45, 45, 90 triangle, so these 2 sides are the same, and the diagonal will be 9 root 2. That one, I'm just using my reasoning. It's nice and fast. And then I'm going to do the same thing. Okay, I have another 45, 45, 90 triangle. So if this is 9 root 2, then this is 9 root 2. And then my hypotenuse will be 9 root 2 times root 2. And simplifying that becomes 9 root 4, which is 9 times 2, which is 18. Okay. We are going to go ahead and skip these. We will come back to them as a warm-up for another day. I want us to take a quick look at one more attached triangle problem here. We're going to look at number 8. So taking a look at number 8, we have 8 has to go here. This is marked as an isosceles triangle, so this also has to be 8. And then these 2 angles are marked as congruent, so they have to both be 45. So I have a 45, 45, 90 triangle. Now I'm going to set up my ratios. 1, 1, root 2. I have x across from the 45 and 8 across from the 90. So if I solve that, I get 8 equals root 2x, which means x equals 8 over root 2. Go ahead, take a minute, try this question on your own, and then check your answer with your group. Now, do be careful and notice that this is not a 45, 45, 90 triangle. This is a 30, 60, 90 triangle. All right, so very quickly, I'm going to go ahead and show you what this would look like. Here we have 5 root 2, which means this is 5, and this is 5. And if I were to then set up my ratios, I would ultimately get 5 over root 2 here. For this one, I have a 30, 60, 90 triangle. This means that my ratio should not be 1, 1, root 2, but should be 1, root 3, 2. So across from my 60 is 8, and my x is across from my 90. So I'm going to go ahead and set up my proportion and solve. So x equals 16 over square root 3. All right. Now, before we wrap up for today, we are going to start talking about some Pythagorean triples, and we will finish talking about this in class tomorrow. So this asks you, what do you notice and what do you wonder? So take a moment, pause the screen, observe what you see in these triangles on your booklet or on the screen, and then come back when you're ready to kind of talk about it. Okay. Now that you're back, hopefully you're noticing that, first of all these triangles are right triangles. They all have, they don't all have the same ratios. Some of them do. When I compare this, 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. So these two triangles are similar by side, side, side. I'm looking at these two triangles. If I multiply this entire triangle by 10, I get another set of similar triangles by side, side, side similarity. Same thing here. If I multiply all 3 sides by 2, I get another side, side, side similarity. And then this one is just alone, 8, 15, 17. What you are actually observing is a set of triangles that are all right triangles, and they are what we call Pythagorean triples. With Pythagorean triples, they are 3 sides of a right triangle where all 3 sides are integers, meaning they are all whole number values, right? This is unique because a lot of times when we do Pythagorean theorem, we get square roots in there, and the square root of a non-perfect square, like the square root of 5, or the square root of 11, or the square root of 12, right? All of those are non-perfect squares. And when we do the Pythagorean theorem with a lot of values, we get these irrational numbers with roots. So when we do a Pythagorean theorem and we get 3 integer values, right, that is what is special about Pythagorean triples. So we're going to take a minute, we're going to put this on our summary sheet, and then we're going to talk about how we can use them. So Pythagorean triples, oops, excuse me, where is your summary sheet? Here it is. So taking a look at your summary sheet, Pythagorean triples are right here after Pythagorean theorem. And some of my classes did already write in your Pythagorean theorem from first semester here. If you did not write in your Pythagorean theorem yet, please go ahead and do that so that you have that summary right here. And then what we're going to do after you take a minute and you write that down is we are going to write down some of our triples. Now, triples are going to be basically a set of 3 numbers that we know work in the Pythagorean theorem. So there's many sets. We're only going to be responsible for a handful. We're going to need to know 3, 4, 5. That's a Pythagorean triple. 5, 12, 13. That's a Pythagorean triple. 7, 24, 25. And 8, 15, 17. There are more Pythagorean triples like 9, 40, 41, or 11, 60, 61, or 12, 35, 37, but we won't bring your work in beyond these 4 sets of triples. So when you know that you have a right triangle and you know 2 sides of the right triangle are these 2 of these values. So let's say you know 2 of the sides of the right triangle are 4 and 5, and the 5 is the hypotenuse. Then you now know that the other leg is a 3. So we're going to use triples. I strongly recommend you just make some flashcards with these 4 sets of numbers, and they're going to become your friend. You're going to see them all the time, and it's going to save you a lot of time. You might be wondering, why couldn't I just go ahead and make a Pythagorean theorem and solve? You absolutely can. It's just going to be more time consuming. So we strongly recommend, because later as problems become more complex, you're going to be using these triples more and more and more, and you're going to be saving a lot of time by doing that. One thing that's important for you to know is that in this 5, 13, 25, and 17, those are all the hypotenuse. So you are going to have in your right triangle a leg, and a hypotenuse. And the biggest number of the set of triples has to be in the position of the hypotenuse, which makes sense because the hypotenuse is the longest side because it's across from the largest angle. So this has to be on the position of the longest side, or the hypotenuse. When we use Pythagorean triples, it also lets us get exact answers. Okay, so let's take a very quick look at how we could use this in our booklet. So on to page 27. Here's a quick page. This is a good kind of practice. So this is something that you're going to kind of memorize or make flashcards for, but then you're going to use it. So I know that there is a triple 5, 12, 13. So the triple is 5, 12, 13. I did not have a dilation factor, so that's the end. I just know that that's side 5. Could I have done a Pythagorean theorem? Yes, but again, it's slower. I strongly encourage you to use your triples by memorizing them. Over here is 7, 24, 25. That's a triple, so I'm going to go ahead and put that in there. Over here on question 3, I don't notice any of my triples having a 10 or a 26. But when I think about it, these are both even numbers, and 10 is 5 times 2. 26 is 13 times 2. And there is a triple that is 5, 12, 13. So I have 5 and 13. So my last side is that 12, but it's also scaled by a dilation factor of 2. So 12 times 2, which is 24. So again, this is 13 times 2. This is 5 times 2, so this is 12 times 2. 5, 12, 13. All right, over here, I'm thinking the same thing. I don't see any triples that have a hypotenuse length of 30. But if I think about this, 30 divides nicely by 6. So I'm going to say that's 5 times 6. 18 is 3 times 6. So there's a scale factor of 6. Do we know of any triple that has a 3 and a 5? Definitely, we have a triple 3, 4, 5. So now I just need to scale that entire thing by 6. So 3 times 6 was 18. 4 times 6 is 24. 5 times 6 was 30. Now, the last thing we're going to do with the triples is I want you to see here that order is important. So I want you to take a look. If you used Pythagorean theorem to solve these, let's not use the triples for a second. If I used Pythagorean theorem, I would do 3 squared plus 5 squared equals x squared, which would be 9 plus 25. So that would be 34 equals x squared. So let's square root that. So we get x equals square root of 34. Whereas here we do 3 squared plus x squared equals 5 squared. That gives me this. 25 minus 9 is 16. So then I get x equals 4. Is the square root of 34 the same as x equals 4? No, it's not. Which goes to show that here we could use a triple, because everything was in the right position. 5 was in the hypotenuse. But here we could not use a triple. Why? Even though it has the same set of numbers, a 3 and a 5, the 5 is in the wrong spot. If this was going to be the triple, the 5 would have to be in the hypotenuse, but it's not. So that tells us that the triple does not apply here. All right, at this point, I'm going to encourage you to start your homework and give some of this a practice, and I will see you later.